and I am happy to address questions or talk about general concepts. We can go over anything in the test if you want. What would you like to do?
Yeah, so I had a question about it's a little bit hard to remember the exact questions, but um
Well, I've got the test here. Let's see. The first test was a system of linear equations, and you were asked to row reduce it. Well, you were just asked, write the augmented matrix and solve it and check, and then do the columns of A span R3 was a question. So let's just take a look. This is the key to the first question. I am going to post this key. I just haven't had a chance to do that yet. So this was the first question where, it was just basically row operations. It took about five or six of those, depending upon how you did them. And because there was a pivot in every row and every column, the columns of A do span R3, and the columns were linearly independent because we didn't have any free variables. It reduced to the identity. Whenever a square matrix reduces to the identity, it means we have a pivot in every row and every column. So having a pivot in every row means AX equal B always has a solution. Asking do the columns of A span R3 is just another way of asking if AX equal B always has a solution for B in R3. So this would turn out to be invertible. We would be able to find an inverse of this original, equation. So maybe that one was not one that you had a question on. Shall we look at the next question?
I think there was a translation
It was a
the re
transformation.
reflection
Oh yeah,
question.
the last question.
Yeah, maybe that one.
Okay.
I think I got it, but
All right. Well, it's a linear transformation that just reflects the vector x about the x1 axis. This is the one that we did in class, the first one. So the point is, if we can figure out what a reflection about the x1 axis does to E1 and what it does to E2, in other words, if we can figure out what T of E1 is, then we have our first column. And if we can figure out what T of E2 is, this is E2, then we get our second column. And of course, E1 sits on the X1 axis. So when you reflect about the X1 axis, nothing happens, right? So E1, you can think of it as the ordered pair 1, 0, or you can think of it as a vector written vertically, 1, 0, just stays right where it is because it's on the X1 axis, right? Whereas the vector E2, which you can think of as the ordered pair, that's up here, 0, comma 1, gets moved down to 0 comma -1 if we take it and just reflect it about this x1 axis. So that builds A. It's always the game is always, hey, let's figure out what the transformation does to E1 and E2, and then we can build the matrix A. And we were kind of
I'm
set.
sorry, one moment. I'm sorry about that.
No problem. I'll pause this. So is this the problem that you're talking about?
I
Well,
can't remember on
well, the
the
thing is, I tried to
test.
set you up for problem 8 by walking you through the process in problem 5. Problem 5 was a linear transformation problem where it's presented differently. I give you the formula for what the transformation does, in other words, how it acts on an ordered pair in R2, something with two coordinates. And this is the formula. It gives us a three tuple, an ordered triple living in R3. So find its standard matrix, and I tell you, hey, if you know what T does to E1 and you know what T does to E2, and I even give you E1 and E2, then we can figure out how to build the matrix, right? So if we just use this formula applied to E1, x1 plus x2, well, x1 is 1, x2 is 0. So the first coordinate of the image would be 1 plus 0, which turns out to be 1. The second coordinate is negative 5 times x2. Well, in E1, x2 is right there, 0. So negative 5 times 0 gives us the second coordinate, which is 0. And the third coordinate is given by this formula, right? And that turns out to be negative 8. That becomes, if you understand enough of, reading and writing matrices notation, that becomes the first column. And then the image of E2, which is 1, negative 5, 2, becomes the second column. So I tried to kind of walk you through it in this problem, and it was a map from R2 to R2, whereas in this problem, it was a map, it was a map from R2 to R3, whereas in this problem, it was a map from R2 to R2. But the point was, since it was mapping out of R2, you apply it to 2 by 1. An element of the domain is a vector that's 2 by 1. Same here. The element of the domain is a 2 by 1 vector, whether we write it as an ordered pair or whether we write it, as a 2 by 1 vector. So there were numerous homework problems where you had to do this.
Yes, so the concept I think makes a lot of sense to me, or in the homework problems, I think I did it correctly. So I'm trying to remember what I put on the test because I know, some of the things I put were probably not correct, but I don't.
Well, hang on. I can pause the recording. I'll pause the recording and I can show you what you did. Okay. So let's say that suppose AX equal B is a system, say a matrix system, where A is M by N. Okay, so let's just think about that. A is M by N. We're going to multiply A times X, so we have to use an N by 1 vector X. And then we get, so these match. And then when we look at the outer dimensions, that feeds us the information about the size of the product, which is M by 1. So T maps from Rn, it takes a vector in Rn and it maps it into Rm. Okay. Now, if AX equal B always has a solution, that means T is onto. Let me just draw a picture to kind of remind you about this concept of onto. Okay, I'll draw these as circles, but a lot of times we draw these spaces, Rn and Rm as some kind of parallelogram. But the idea is this. We have x's over here and we have b's over here. And multiplication by a or applying the function t are the same thing. And onto means that no matter what b you pick over here in the codomain, that there's always an x back here that will hit it. There's always a preimage. See, so onto means no matter what element of the codomain, that's the domain you're shooting at, no matter what element you look at, you can find a domain value that will map to that. So that's what I think about. I think about covering up the codomain. Every one of these points gets covered up with an arrow. See what I mean? That means no matter what B we pick, there's an X back here so that T of X, which is AX, will hit B. So these mean the same thing. Does that make sense?
Yes.
Okay, and the bottom line is A must have a pivot in every row. Now we may not be able to see that until we do row reduction, but the pivot positions don't actually change. Once we find the pivot positions, then we can say, oh, those were the pivot positions back in the original matrix. So, for example, I'm looking for this particular problem. When we found, oh, there was not a pivot in every row. Okay, this turned out to be a 3 by 2. Okay, because we're right because if it's going from R2 to R3, then A has to be a 3 by 2 because if we want to multiply A times X, well, X is coming out of R2, so we know it's a 2 by 1. Okay, so A has to be a 3 by 2. Okay, there's not a pivot in every row. Theorem 4 tells us, oh, that means there are going to be some vectors B in R3 that we cannot construct using a linear combination of the columns of A. And you can just look at the columns of the row reduced A, you know, and you can see, oh, there's an issue there. I mean, these, if you call this A and you call this, U for echelon form, like we're doing right now, there are vectors that we cannot build using the columns of U. That means the same goes for A because these have exactly the same solutions. We know that elementary row operations do not change solution sets. So the 1 and the -5 that we realized are the pivot positions here in the row reduced A, it's not completely reduced, but we performed some operations, are exactly the same as the pivot positions back here in A. We're going to talk about that more, but that's what it turns out to be. And there is no pivot in row 3, so AX equal B does not always have a solution. It's got a solution for some vectors in R3, but not all of them. So T is not on 2. This was theorem 4. But when you look at this row reduction, there is a pivot in every column. So we don't have any free variables. So that means, oh, it's 1-to-1. So if AX equals B has infinitely many solutions, and if that happens, it actually means AX equals 0 has infinitely many solutions because the geometry of the solution set to AX equals 0 is the same as the geometry of the solution set to AX equal B when B does have a pre-image set. When there are solutions for B. We know there are always solutions to AX equals 0. But if AX equals 0 has infinitely many solutions, so it's almost easier just to think about the homogeneous situation, then T is not 1-to-1. And that means A cannot have a pivot in every column. You got some kind of free variable going on to generate infinitely many solutions. Does that help?
Yes, I think it definitely helps. I'm not sure why I wrote what I did on my exam, but
Well,
um,
I mean, it's okay. I think that taking an exam is stressful at best, right? I,
yeah. Um,
I think you just mixed up linear dependence of the columns of A with
yeah.
onto when linear dependence of the columns of A is related to one-to-oneness.
Yeah, I think that's yeah, definitely a mistake that I made there. Is it also can R2 ever be onto R3?
That it sure cannot
So
be.
that's part
We
of
talked
the
about that.
yeah. So I tried to give that justification because I know it's going R2 to R3, the input of
You did actually. You did. You just weren't addressing, well, okay, so you gave me something that wasn't related, but if you hadn't said something that was just wrong, I wouldn't have had to take off. Like I could have given you half credit because you did say also R2, and I know you understand R2 to R3 is never onto. And that's right, because you understood the geometry of that. If you had just said that R2 to R3 is never onto, I could have given you credit. But you said something that was just wrong uh, by saying that the columns of A were linearly dependent. They're not because we had a pivot in each column. So I had to balance that you said, something that was actually wrong in addition to saying something that was right. It was kind of a wash. But I could probably change that and give you two more points for that. I can do that.
it's up to you. I think I mean I understand I understand that
I
how
mean, I
that's
just try
graded.
to
That
be
makes
fair,
sense.
but you're taking the time to come in and discuss it. And I do remember that you really understood that R2 cannot be on to R3. Like you got that. Whether or not you mixed it up with linear dependence and independence of the columns is another question. So, no, I think I can give you half credit for that. And here, the columns of A may or may not be linearly independent. It depends upon the size of A, right? Like if A has a pivot in every row and the number of columns is less than or equal to the number of rows, then we've got a pivot in every column and we've got linear independence. You see what I mean? And so, but if we've got more columns than rows, then we can have a pivot in every row and still not have a pivot in every column. See what I mean? So it really just depends on the size of A, whether it's square or whether it's got more rows than columns. So here, kind of similarly, let's say we know the columns of A are linearly dependent. Well, depending upon the size of A, you know, A may or may not have a pivot in every row. It just depends upon A. See what I mean? So you just want to kind of remember when we're looking at pivots in rows, we're talking about onto. Think about kind of going across, onto. And then if we're talking about pivots in columns, we're talking about linear dependence versus independence of the columns, and we're talking about one-to-oneness. Because the minute we have infinitely many solutions, then we can use one of those solutions to build a linear dependence relation. Should we talk about that? I think there was a question that where I asked you to come up with a linear dependence relation. Let's see if we did that okay. I asked you to come up with a specifics. I kind of tried to lead you to it. Yeah, yeah, okay. So let's look at that problem. Uh, because it's all kind of related. It's all interrelated. Look at problem number 2. Let me see if I can grab that. Okay. So I really tried to kind of sneak up on stuff with you. Like I tried to kind of walk you into the correct thinking as best I could, whether or not I succeeded, that, well, I guess I didn't for some people. This one was super easy to row reduce, right? It just took 2 row operations and all of a sudden, we only have one pivot position, right? And we have 2 free variables, right? Well, that actually means back here in A, there's only one pivot position as well. And we'll discuss that. But anyway, when you teased out the solution, I was a little disappointed that people were still having trouble with this kind of thing. Let's just look at this, okay? We wanted to get a leading 1 here, so we just divide that top row by 3. All right. So let's say that you did that, and I think you did do that correctly. Now we got to interpret this. Let's just see, read it off. The first equation says x1 minus 4/3 x2 minus 1/3 x3 equals 0. So we bring over the minus 4/3 x2 to the other side as a plus 4/3 x2. We bring the minus 1/3 x3 over to the other side. See, this is all equal to 0 here, right? To the other side, and we get this expression for x1. Okay, that's fine. But these aren't zeros. Okay, just because x2 is free doesn't force it to be 0. We just don't know what it is. It's just something. It could be anything. And x3 is free, but it doesn't make it 0. In fact, we have to hold a spot for x2 in the x2 position, and we have to hold a spot for x3 in the x3 position using a 1. See what I mean? Like when we tease the x2 out of, these 3 things, well, there's 4/3 of an x2 in the first position. There's 1 whole x2 in the second position. There aren't any x2s in the third position, okay? In the third coordinate. Same with x3s. There's 1/3 of an x3 in the first coordinate. There aren't any x3s in the second coordinate because that's where x2 is living. And there's 1 x3 in the third coordinate. See what I mean? So, you lost a couple of points not understanding how this works. And I'm not really sure how that could happen. And if you do, I don't know, maybe y'all get too many shots at the homework, or maybe somehow the homework you're doing it and not understanding what you're doing. I just don't know. But you were not the only one, but not by a long shot. Now, once we have some kind of expression, for the general solution with these parametric variables, we usually just rename the x sub i's, with letters. Okay, that's not a big deal. It's just a thing. Then we want to find a specific solution. Now let's just remember what that means. When we drop in a particular value, for x2, which I'm calling s, and a particular value for x3, which I'm calling t, even if you just kept calling them x2 and x3, I don't care. You could find a specific solution. And I picked 0 for t because that's just easy. I just get to ignore this and just deal with this. And I picked 3 because then it made all of these values integer values. Okay. Now let's just think about what that means. When we say x is a solution to ax equals 0, it means we have found weights that can weight these columns so that the weighted sum of these columns builds the 0 vector, which has zeros in every coordinate, right? Well, that's what a solution to ax equals 0 does by definition. It means when we multiply a times this x, we get the 0 vector. Well, that means, multiplication, ax. The first definition of matrix vector multiplication is the first coordinate of x weights the first column of a. Okay, so I mean, when these are the columns of A, these we usually, in theory, call them scalars, C1, C2, C3, but they are the coordinates of the X that work to build the zero vector when they're used, when those coordinates are used as weights for the columns of A. Does that make sense? I mean, you can check this. I mean, check it out. Now, A times X is, by definition, column A1, column A2, column A3 of A times X1, X2, X3. Now just think of these are column vectors, okay? Each one of these is a 3 by 1 vector. Well, by definition, that is X1 scaling the vector A1 plus X2 scaling column A2 plus X3, maybe positive or negative, but we say plus, and then the value of X3 is either positive or negative, scaling A3. Okay, so these are the weights X1, X2, X3, which are also called C1, C2, C3. They're just values. So I just grabbed my specific solution and wrote a linear dependence relation. You could have guessed one. You could have guessed just by looking at it that this column would be what? The like, let's see, what would we have to multiply 3 by to get -4? Or maybe it's even easier to relate column 1 and column 3. What would we have to multiply 3 by to get -1? Like to show that this column is a scalar multiple of that column, we would multiply 3 by -1/3. Well, then we check and we multiply -9 by -1/3. Oh yeah, that's 3. Multiply -6 by the same scalar, -1/3. That builds 2. So you could have just kind of examined this and said, oh, or you could say, hey, if I take column 3 and multiply it by -3, I get column 1. You could have built it just by inspection. Or you can just pick up a solution to AX equals 0, and that gives you because of this, the definition of what it means to multiply A by X, you know, and that this turns out to be the zero vector. Remember, this is a vector. It's a 3 by 1. This is a 3 by 1. This is a 3 by 1. This is a 3 by 1. I hope that helps.
I think it does help a lot.
Turns out both of these columns are scalar multiples of the first column. It's almost easier to see that both of these columns, column 1 and column 2, are scalar multiples of column 3, right? You can, multiply column 3 by what? -4 and get column 2. You can multiply column 3 by what? -3 and get column 1. Well, that means you can multiply column 1 by the reciprocal, right? -1/3 and get column 3. See what I mean? And you could multiply column 1 by what? -4/3 and get column 2. The point is, these columns are all lying on the same line in 3 space. They're all scalar multiples of each other. So you only need one of them. Like all the information of A is held in just one of these columns because the other 2 columns are redundant. And so that's why the span of all 3 of them is the same as the span of 2 of them, which is the same as the span of one. I could have put any 2 here and any of the ones here. And this would still be a true statement. That's what it means to have 2 parametric variables. It means, well, if there are 3 columns and we have 2 parametric variables, then we only actually need one of the columns because 2 of them are dependent on the one. That's what having parametric variables means. It means we can write linear dependence relations between the columns. And this, even if you got the answer, the general solution, to AX equals 0 incorrect. I was hoping people, like I tried to make it so you could get partial credit, you just take the general solution to AX equals 0 and add any solution to AX equal B. I give you one. I said, hey, I don't even know what B is, but the solution to AX equal B is this vector X. If you add a particular solution to AX equal B plus the general solution to AX equals 0, that gives you the general solution to AX equal B. Now, this is one of them, but it's one of them plus anything in this entire plane. So we're shifting this plane by this. It's a shift, remember? If this is here's 0. So here's the planar solution to x equals 0. Just shift it through space by this vector x. And then you get the plane that's the solution to ax equal b. 0 would map to x.
Well, thank you for the that explanation. I think conceptually I wasn't as far off as I thought, but I think maybe I'm having a lot of trouble with the notation that I need to get
Yes,
down.
yes. And you know what? Yeah, that's right. It's all about reading what it means. Like when I write all this stuff in a test, I'm trying to point you, it's almost like a learning opportunity, right? Like point you to a moment where you can practice reading hard, if that makes any sense. And it is about the notation because in mathematics, notation is everything. Mathematics is a language. And gosh, linear algebra's got plenty of it, plenty of it. But I will add something to your grade because I do now remember that we discussed that one concept that, yeah, no, Rn cannot map on to Rk if k is bigger than n. It's impossible. There just aren't enough points. And you did great on that last problem. You did that one just fine with the reflection about x1. You got, full credit for that. And
Okay.
I think you're right. I think, but you did admirably, honestly. You really did. I would,
Um, well, yeah, I think I was close. So I'm not uh I think next test I'll come back and do better, so we'll see. But yeah, thank you for the extra explanations. I think it really helped me um kind of figure out what I might be lacking, if that
well,
makes sense.
let's do this more often, like, not just the night before test two, but let's try to do this, every week. You can just reach out to me like you did today and ask for a time. And if I can do it, I will do. And I'm up in the morning too, it could be before class, it can be in the evening, it's just random times, Friday afternoons, just and let's just have discussions, just open discussions, and it generates a nice little video for other people that are listening in, later. So you're doing a service by saying, I want an office hour in Zoom. Think about it that way.
Well, well, thank you.
You're
Yeah,
welcome.
I definitely appreciate the extra time because it is super helpful. Um, just yeah, it helps